Variation of parameters is yet another method to solve non-homogeneous equations. Now, this particular method depends on the Wronskian, which is a matrix, and finding its determinants. So we will only focus on second order and third order differential equations. I'm going to give the background for a second order differential equation and extend the idea to a third order differential equation. So what is the method about? As I mentioned, we are going to consider a second order differential equation first, a non-homogeneous equation first, and then we can move on to a third order differential equation, and that would be good enough. So consider a second order non-homogeneous d, and we all know that is of the form a2x, the second derivative, a1x, first derivative, a0x, y, equals some function g of x. And that is a non-zero function. And that is what would make a DE non-homogeneous. And we know non-homogeneous equations has a solution of the form y equals yc plus yp. Now, in a homogeneous equation, yp is 0, so we simply have the complementary function. So the particular solution is a characteristic of a non-homogeneous DE. So just to recap, this is the complementary function or complementary solution, and yp is the particular solution. Now, we know for a second order DE the complementary solution is obtained by solving for the associated homogeneous equation, and we know the solution is of the form yc equals c1 y1 plus c2 y2. Naturally, both y1 and y2 will satisfy the DE, ergo yc will satisfy the DE also, because that is a linear combination of y1 and y2. That said, when we find the solution, we actually know what y1 is and what y2 is, because we solve the homogeneous equation and we end up getting y1 and y2. Now we're going to make use of y1 and y2, sort of go along the ways of reduction of order and find a particular solution. So let us assume that, well, before we get to that step, let us rewrite the DE as follows. So we have a2x y double prime plus a1x y prime plus a0x y equals g of x. Let's divide by a2x. Would equal g of x by a2x. This is quite important. So the standard form that we want is y double prime plus, call this part as some function p and that as some function q. I don't want to write it as p of x and q of x because it gets really messy, so I'll just call it as p and q. Just keep in mind that both of them are functions of x, which is the independent variable, and that would equal just some of the function f of x. Since we know y1 and y2, the particular solution is a linear combination of y1 and y2. But we don't have arbitrary constants in the particular solution, rather we have functions of x, because the particular solution cannot have arbitrary constants. That said, our objective is to find u1 and u2. We know y1 and y2 already, so if we found u1 and u2, then we have the particular solution. So that is our goal. So the objective is to find u1 and u2. So how do we go about doing this? Well, the particular solution is going to satisfy the DE. So let us find yp prime. We have to use product rule here, so u1 y1 prime plus y1 u1 prime plus u2 y2 prime plus y2 u2 prime. That's the first derivative. The second derivative is going to get lengthy. So u1 y1 double prime plus y1 prime u1 prime plus y1 u1 prime plus u1 prime y1 prime plus u2 y2 double prime plus y2 prime u2 prime plus y2 u2 double prime plus u2 prime y2 prime. So all I did is that part is product rule applied. So apply product rule to that part, you get that. Apply product rule to that part, you'll get that. Apply product rule to that part, you'd get that. And apply product rule to that part, you'd get that. So I pretty much am applying product rule. The first derivative is quite obvious, I just used product rule twice. The second, if you match the colors, you'd get the idea. So that said, we can take yp double prime, yp prime, and yp and plug it in the given DE because it is going to satisfy the equation because it is a particular solution. So plug in yp, yp prime, and yp double prime in the DE. So we would end up getting u1 y1 double prime, y1 prime u1 prime, y1 u1 prime, u1 prime y1 prime plus u2 y2 double prime, y2 prime, u2 prime, y2 u2 double prime, u2 prime, y2 prime, plus p times the first derivative, which is u1 y1 prime, y1 u1 prime, u2 y2 prime, y2 u2 prime. And lastly, q times y, which is simply y1 u1 plus y2 u2, and that is equal to f of x. And that's what we would have. Now, I'm going to gather some terms, so I'm going to gather u1 y1 double prime, u1 y1 prime, and u1 y1. So I would have u1 y1 double prime plus p y1 prime plus q y1 multiplied by u1. Likewise, I am going to pick u2 y2 double prime and u2 y2 prime and u2 y2. So I would have u2 multiplied by y2 double prime plus p times u2 y2, p times y2 plus q times y2 prime, q times y2. Now, the remaining terms, we can just write that here. So y1 u1 prime plus y1 or y1 prime u1 prime, y1 u1 prime, u1 prime, y1 prime, y2 prime, u2 prime, y2 u2 double prime, u2 prime, y2 prime, plus p times y1 u1 prime, y2 u2 prime equals f of x. Those are the terms that are left over. Now, you may say, well, why did this guy group it this way? Well, we know y1 and y2 are solutions to the associated homogeneous DE. Therefore, when we plug in the solution to the homogeneous DE in the DE, that should become 0 because that is a homogeneous DE. So this we would have y1 double prime, y1 prime, plus p times y1 prime, plus q times y1 would be 0. And the second solution, when we plug it in the DE, that would become 0, leaving us with only the remaining terms, which would be y1 prime, u1 prime, y1 u1 prime, u1 prime, y1 prime, y2 prime, u2 prime, y2 u2 double prime, u2 prime, y2 prime, plus p y1 u1 prime plus y2 u2 prime. I am quite sure that I missed out a double prime here. This should be double prime. I think we are okay. So, I am going to write that part as d over dx u1 prime y1. Okay. Keep the other terms as is. And write that term u2 prime y2 plus the remaining terms p times y1 u1 prime y2 u2 prime equals f of x. We can combine. So what did I do? I simply did reverse product rule. So if you apply product rule to this term, you'd get that term, So I just did product rule in reverse, same here. Product rule in reverse. I can combine the two derivatives and write it as u1 prime y1 plus u2 prime y2 plus p times y1 u1 prime plus y2 u2 prime plus u1 prime y1 prime y2 prime u2 prime equals f of x. Now we have to make a few assumptions here in order to get a solution. So what I'm going to do, I am going to assume u1 prime y1 plus u2 prime y2 equals 0. Which would automatically imply u1 prime y1 prime plus u2 prime y2 prime equals f of x. So if I assume that term would go away, that term would go away because they are the same. So if my assumption holds true, then the second part would hold true also. Now I would end up having y1 u1 prime y2 u2 prime equals 0, y1 prime u1 prime y2 prime u2 prime equals f of x. Now in matrix form we could write this as y1, y2, y1 prime, y2 prime multiplied by u1 prime, u2 prime equals 0 and f of x. Now, we all know that this is a system of linear equations. If you recall algebra, what we have here on this side is a matrix, and I wrote it in terms of u1 prime and u2 prime. Our goal is to solve for that. Of course, we can invert the matrix and, find the solution, but if you observe closely, that is the Wronskian. And we know for linearly independent solutions, the determinant of W, which we write it in short notation as that, is not equal to 0. And clearly, the solutions y1 and y2 are linearly independent. But every single method that we've seen, we made sure that the solution to the homogeneous equation is linearly independent. So since the determinant is never going to be 0 in our case, we can use a different technique, computationally expensive, but we can use a different technique to find the solution to u1 prime and u2 prime. So what is that technique? So that technique is called Kramer's rule. Now, this is something that people must have covered in linear algebra or college algebra or calculus 2 perhaps, or calculus 3, or matrix analysis. So what does the Kramer's rule state? If we want to find the solution to u1 prime and u2 prime, we've got to do two things. We take the right-hand side, 0 f of x, and plug in the first column. I would get the matrix W1. We take the right-hand side and plug in the second column. I'll get that matrix. So the solution to u1 prime is simply determinant of W1 divided by the determinant of Wronskian. And the solution to y2 prime is the determinant of W2 divided by the determinant of W. The denominator should never equal to 0. It will never equal to 0 because we have linearly independent solutions, which would guarantee that the determinant of the Wronskian is not equal to 0. We know how to find the determinant. u1 prime is simply 0 times y2 prime minus y2 times f of x divided by the determinant of w. And u2 prime is y1 f of x minus 0 y1 prime divided by the determinant of w. And we know the determinant of w is simply y1 y2 prime minus y2 y1 prime. That comes from the original matrix. So u1 prime is negative y2 f of x divided by the determinant of w, and u2 prime is y1 f of x divided by the determinant of w. Now, this is an easy formula for second-order differential equations, but for third-order differential equations, when we extend this idea and we extend this concept, I don't want you to simply memorize the solution. You have to evaluate the Wronskian, its determinant, and the W1 and W2 matrices. So we have u1 prime and u2 prime, which would mean u1 is the integral of minus y2 f of x divided by the determinant of the Wronskian dx, and u2 is simply integral minus y1 f of x divided by the Wronskian of dx. Now, key thing to notice here is when we integrate, of course, we would have integration constants. We don't need those constants of integration. As they will get combined into the constants in YC. They simply will. So what is the particular solution? So the particular solution YP is simply u1 y1 plus u2 y2. That is it. Now, how do we extend this to a third order equation? So a third order non-homogeneous DE. If we have a third order non-homogeneous DE, we would end up having a3x y triple prime, a2x, y double prime, a1x, y prime plus a0x equals a0xy equals some function g of x. And we do require the constraint that we divide a3 out. We have to, or else the method will not work. So we can divide it write it like so, which would simply give me the third derivative, some p1 second derivative, some p2 first derivative, some p3 y equals f of x. So this would result in a system of equations. It will follow the exact derivation that we did here. It's just painful. So we would go directly to the generalized solution. What we have defined are three matrices. The first matrix would be 0, 0, f of x. And we have y2, y2 prime, y2 double prime, y3, y3 prime, y3 double prime. And you may say, well, why do we have y3? This is a third order equation. So note, well, I'll write this note later on. W2 is y1, y1 prime, y2, no, y1 double prime, y2, y2 prime, oops, 0, 0, f of x, y3, y3 prime, y3 double prime, and lastly w3 would be y1, y2 prime, no, take that back, y1 prime, y1 double prime, y2, y2 prime, y2 double prime, 0, 0, f of x. y1, y2 and y3 are linearly independent solutions in the complementary solution, i.e. yc is c1 y1 plus c2 y2 plus c3 y3. So now that we have the three matrices, the Wronskian, since we have three functions, is y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, y3 double prime. And the solution to u1 prime, u2 prime, and u3 prime are u1 prime is the determinant of w1 divided by the determinant of the Wronskian. u2 prime is the determinant of w2 divided by the determinant of Wronskian. u3 prime is the determinant of w3 divided by the determinant of the Wronskian. We have those three solutions, which would mean u1 is simply integral of the determinant of w1 divided by the determinant of the Wronskian dx. u2 is integral determinant of w2 divided by the determinant of Wronskian dx. u3 integral determinant of w3 divided by the determinant of w dx, or any independent variable, and the particular solution would simply be u1 plus u2 plus u3. Forgot to multiply. So we've got to go back to our substitution. So by plugging the substitution back in, we would have y1 u1 plus y2 u2 plus y3 u3 as the particular solution. Again, the particular solution does not depend on arbitrary constants. So that said, we can move on to an example and we'll try to solve this using variation of parameters. So the right hand side is f of x. The associated homogeneous equation is y double prime plus y equals 0. The auxiliary equation here is m squared plus 1 equals 0, which would simply imply m squared equals minus 1. So m1 would be plus I, m2 minus I, therefore alpha is 0, beta is 1. The complementary solution is y equals c1 cosine x plus c2 sine x. Now we have the complementary solution and we know what y1 is. y1 is cosine x and y2 is sine x. So we can form the matrices. W is the Wronskian, so we have cosine x, sine x, minus sine x, cosine x. So the determinant of the Wronskian would simply be equal to cosine x times cosine x minus sine x times sine x. So we will have cosine squared x plus sine squared x, and if you know the identity, that is 1. Now w1 would simply be equal to 0, and the f of x here is secant x, sine x, cosine x. So the determinant of w would be 0 minus secant x times sine x, which would simply be minus tangent x, the determinant of w1. The determinant of w2, we can find it after we find what w2 is. y1, have it backwards, my bad. y2 and y2 prime. Yeah, I had it right. And here we'd have cosine x minus sine x, 0 secant x. The determinant of w2 would simply be cosine x times secant x minus 0, which would simply be cosine x times 1 over cosine x, which is simply 1. That was easy. So u1 is determinant, or u1 prime is determinant of w1 divided by the determinant of w, which is negative tan x, divided by 1. u2 prime is the determinant of w2 divided by the determinant of w, 1 over 1, we have 1. This would mean u1 is integral minus tangent x dx. u2 is integral 1 dx. Integral of tangent x is secant squared x, so we have negative secant squared x, and u2 is equal to x. So the particular solution is simply u1 y1 plus u2 y2. So we have u1 is secant squared x times cosine x plus x times sine x. If we simplify, the particular solution would be minus cosine x plus x sine x. Oh, sorry, it's 1 over... So I paused for a second because I didn't expect to see cosine x because we already have cosine x. So the answer actually is secant x, if you simplify the first term. So the solution to the DE is y equals c1 cosine x plus c2 sine x minus secant x plus x sine x. A similar problem here. The function f of x is sine x. That is a non-homogeneous equation. The associated homogeneous equation is y double prime plus y equals 0. Therefore, the auxiliary equation is m squared plus 1 equals 0, which would imply m squared equals minus 1, m1 is I, and m2 is minus I. So the complementary solution is yp, yc equals c1 y1 plus c2 y2. We know alpha is 0, beta is 1, so yc is c1 cosine x plus c2 sine x. So it's very similar to the previous problem. So from the previous problem, we know the determinant of w, that is not going to change. The determinant is not going to change for w. It's 1. However, w1 will change because we're going to plug in 0 and sine x now. And here we have sine x and cosine x. So the determinant is negative sine squared x. W2 is 0 and sine x. And we have cosine x and sine x there, which would give us sine x cosine x. Now we have to integrate, so u1 prime is simply the determinant of w1 divided by the determinant of w dx, u2 prime integral determinant of w2 divided by the determinant of w dx. So u1 prime is integral sine squared x dx, and u2 prime is integral sine x cosine x dx. Using the trigonometric identities, one minus 2 sine squared x is cosine 2x, and 2 sine x cosine x is sine 2x. So I can rewrite the integrals as, sorry, that has to be u1 not u1 prime, and u2 not u2 prime, because u1 prime is the determinant of w1 divided by w, and u2 prime is the determinant of w2 divided by the determinant of w. So u1 would equal negative 1 minus cosine 2x divided by 2 dx. u2 would be integral sine 2x divided by 2 dx. We will get negative x over 2 plus sine 2x over 4 for u1, and u2 would be negative cosine 2x over 4. So the particular solution, yp, is u1, y1. We know what y1 is. It is cosine x. So minus x cosine x over 2 plus sine 2x cosine x over 4 minus cosine 2x y2 sine x over 4. And the solution to the dE is c1 cosine x, c2 sine x, minus x cosine x divided by 2 plus sine 2x cosine x over 4 minus cosine 2x sine x over 4. I wonder if I could simplify this further. Something tells me that we can. Let's see. So y is c1 cosine x plus c2 sine x minus x cosine x over 2. Sine 2x is 2 sine x cosine x times cosine x over 4. And cosine 2x, I could write it as 2 cosine squared x minus 1. Yes. Multiplied by sine x divided by 4, which would give me c1 cosine x plus c2 sine x minus x cosine x over 2 plus 2 sine x cosine squared x over 4 minus 2 cosine squared x sine x over 4 plus sine x over 4. These two would get cancelled. So we have c1 cosine x. Keep in mind, we can't leave that sine x over 4. That would be linearly dependent on that. But we can combine the two. If we pull sine x out, we have c2 plus 1 over 4 minus x cosine x over 2, which would give us c1 cosine x plus some of the constants c3 sine x minus x cosine x divided by 2. So here we have a second order DE, non-homogeneous, that is f of x. The associated homogeneous equation is m squared minus 4 equals 0, which would imply m plus 2 times m minus 2 equals 0, which would imply m1 is 2 and m2 is minus 2. So the complementary solution is y equals c1 e raise m1x plus c2 e raise m2x, and that's what we have. So now we know y1 is e raised 2x and y2 is e raised minus 2x. So first we start with the Wronskian, e raised 2x, 2 e raised 2x, e raised minus 2x, 2 e raised minus 2x, minus 2, sorry. So the determinant of w would be equal to negative 2 e raised 2x, e raised minus 2x, negative 2 e raised 2x, e raised minus 2x, which would give us negative 4. w1, 0, e raised 2x over x, e raised minus 2x, minus 2 e raised minus 2x, which would imply the determinant of w1 is e raised 2x, e raised minus 2x divided by x. We will get 1 over x. w2 is e raised 2x, 2 e raised 2x, 0 e raised 2x divided by x. w2 would be equal to e raised 2x times e raised 2x over x, which is e raised 4x over x. Which would imply u1 prime is the determinant of w1 over the determinant of w, and u2 prime is the determinant of w2 divided by the determinant of w, which would imply u1 is integral negative 1 over 4x dx, and u2 is integral e raised 4x divided by x dx. Now, the first integral is easy. We'll simply have negative 1 over 4 ln of x. The second integral, however, we cannot integrate that. We have to do it numerically. But we can write it using fundamental theorem of calculus. We can rewrite it as integral some constant x naught to x e raised 4t over t dt. And we will just leave it as is because we cannot integrate. This is using fundamental theorem of calculus. Or you can just leave it as an integral. It's entirely up to you. So yp, the particular solution, is negative 1 over 4 ln of x multiplied by e raised to x plus u2 e raised minus 2x. We will just leave it as is. So the solution to the dE is y equals c1 e raised to x, c2 e raised minus 2x, minus 1 over 4 ln of x e raised to x, plus u2 e raised minus 2x, where u2 is integral x naught to x e raised 4t over t dt, or you can simply write it as integral e raised 4x over x. The correct approach would be to have it this way. And that would be the solution. Here we have a non-homogeneous equation with a hyperbolic sign. If you don't know the derivative or integral of a hyperbolic sign, you could always refer to the table at the beginning of the textbook, or you could look it up online. It's very similar to sine and cosine. It's very straightforward. So the associated homogeneous equation is y double prime plus 2y prime plus y equals 0. So the auxiliary equation is m squared plus 2m plus 1 equals 0, which if you factor, we would have m plus 1 times m plus 1 equals 0. Therefore, m1 is minus 1 and m2 is minus 1. And those are repeating roots, therefore the complementary solution is y equals c1 e raised m1x, which is minus x, plus c2 x e raised minus x. Do not forget the methods that we've done in the past. If we have repeated roots, we've got to multiply by x, x squared, and so forth. So this would imply y1 is e raised minus x, and y2 is x e raised minus x. So the Wronskian w is e raised minus x, x e raised minus x. Over here we'd have negative e raised minus x, negative x e raised minus x, plus e raised minus x, which would imply the determinant of the Wronskian is e raised minus x, multiplied by minus x e raised minus x, plus e raised minus x, minus x e raised minus x, multiplied by minus e raised minus x. So we will have minus x e raised minus 2x plus e raised minus 2x plus x e raised minus 2x. Those two would go away. We simply have e raised minus 2x. W1 is sine h 2x zero sine h2x and x e raised minus x and minus x e raised minus x plus e raised minus x, which would give us the determinant of w1 equals x e raised minus x multiplied by sine h2x. Now you look at that and you say, oh, that's just too complicated. It is not. Sine h2x can be written in terms of exponentials as e raised to x minus e raised minus 2x divided by 2. Likewise, cosine h2x is simply e raised to x plus e raised minus 2x divided by 2. That is for future reference. So if I rewrote sine h2x in terms of the exponentials, I'd have x e raised minus x, e raised to x minus e raised minus 2x divided by 2. So that would reduce to x over 2 times e raised x minus e raised minus 3x. And we've got to divide that by the determinant of w, which is e raised minus 2x. So x over 2 e raised x minus e raised minus 3x divided by e raised minus 2x. X over 2 e raised 3x minus e raised minus x. So that is u1 prime, and u2 prime is determinant of w2 divided by the determinant of w. So we've got to find w2. So the determinant of w2 is e raised minus x sine h2x. We can use the same trick that we used before, convert it to exponentials. Divided by 2 and distribute. That has to be positive. And we divide the determinant of w2 divided by the determinant of w. So 1 over 2 e raised x minus e raised minus 3x divided by e raised minus 2x, which would give us 1/2 e raised 3x minus e raised minus x. Now we have to integrate to find u1 and u2. So u1 is integral x over 2 e raised minus 3x minus e raised minus x dx. And we've got to use integration by parts to get the answer. Oh, sorry, it's e raised positive 3x. So 1/2 x e raised 3x divided by 3 minus e raised 3x divided by 9 minus 1/2 x e raised minus x divided by minus 1 minus e raised minus x. That would give us 1/2 3x e raised 3x minus e raised 3x divided by 9. We have a negative in common, so we could do 1/2 x e raised minus x minus e raised minus x. That would be u1, and u2 is integral 1/2 e raised 3x minus e raised minus x dx. That would give us 1/2 e raised 3x over 3 plus e raised minus x over 2. So the solution now, the particular solution, is yp equals u1 y1 plus u2 y2. And we know what y1 and y2 are, so we have 1/2 x e raised minus x minus e raised minus x multiplied by e raised minus x, and 1/2 x e raised minus x minus e raised minus x. Oh, sorry. Forgot the first term. So we have 1/2 3x e raised 3x minus e raised 3x divided by 9 multiplied by e raised minus x plus 1/2 x e raised minus x minus e raised minus x multiplied by e raised minus x plus 1/2, this would be u2, e raised 3x over 3 multiplied by e raised minus x times x plus e raised minus x over 2 multiplied by e raised minus x times x, because y2 is x e raised minus x. Distribute and simplify. We have 1/18 times 3x e raised 2x minus e raised 2x over 18 plus x e raised minus 2x over 2 minus e raised minus 2x over 2 plus 1/6 x e raised minus x and 3x, that would become 2x. And another term, we have e raised minus x times e raised minus x, e raised minus 2x times x over 2. We can combine the terms now. If I combine that term with that term, I would get x e raised minus 2x. I can combine that term with that term. That would give me 2/6 x e raised 2x. And lastly, we can combine the other two terms. I would have minus e raised 2x over 18 minus e raised minus 2x over 2, which would give us x e raised minus 2x plus 3x e raised positive 2x. We would leave the rest as is. So the solution to the DE is y equals c1 e raised minus x, c2 x e raised minus x, plus x e raised minus 2x, plus 3x e raised 2x, minus e raised 2x over 18, minus e raised minus 2x over 2. Here we have another non-homogeneous dE. The associated homogeneous equation is m squared plus 1 equals cosine squared x. The roots are m squared plus 1 equals 0, which would imply m is plus or minus I, which would mean alpha is 0 and beta is 1. The complementary solution would then be y equals c1 cosine x plus c2 sine x. So we have to find the particular solution now. So in order to do that, we are going to use y1 and y2, y1, y2. So the Wronskian is cosine x, sine x, minus sine x, cosine x. The determinant of the Wronskian would be cosine squared x plus sine squared x, which would give us 1. W1, the matrix W1, is 0 cosine squared x, sine x, cosine x, which would imply the determinant of W1 is negative sine x cosine squared x. U1 prime is the determinant of W1 divided by the determinant of W, which in this case is simply 1. So we have minus sine x cosine squared x. W2 is cosine x sine x with a negative 0 and cosine squared x, which would simply mean determinant of W2 is cosine cubed x. So U2 prime is the determinant of W2 divided by the determinant of W, which would give us cosine cubed over x over 1, which is cosine cube x. So U1 is integral of U1 prime, which is minus sine x, cosine squared x dx. We could use substitution, cosine x. Du is negative sine x dx, which would give us u squared du, u cubed over 3. So we would have cosine cubed x over 3. That would be the solution to u1. u2 is integral cosine cubed x dx. Now, the best way to integrate this is to rewrite it as cosine x minus sine squared x dx, distribute the cosine x, we would have u2 equals sine x. U substitution again, we could say u as sine x, du is cosine x dx. So we have minus integral u squared du. We have sine x minus sine cubed x over 3. So now the solution, the particular solution, is yp equals u1y1 plus u2y2. What we have is cosine cubed x over 3 times cosine x plus sine x minus sine cubed x over 3 times sine x, which we could write as 1 over 3 cosine raised 4x plus sine raised 4x plus sine squared x over 3. Now, could we simplify this? We can, but I guess we'd just leave it as is. It's too much trouble, so we'll just leave it as is. So, the solution to the DE is y equals c1 cosine x plus c2 sine x plus 1 over 3 cosine raised 4x plus sine raised 4x plus sine squared x, and that would be it. Here is another second order non-homogeneous DE, and in this case the independent variable is t, not x. The associated homogeneous equation is 2y double prime plus 2y prime plus y equals 0. The auxiliary equation is 2m squared plus 2m plus 1 equals 0. I believe we can factor this as 2m squared plus m plus 1. Perhaps not. Let's do a quadratic formula. M would be equal to minus b plus or minus b squared minus 4 times a times c divided by 2a minus 2 plus or minus square root of negative 4 over 2 times 2, which is minus 2 plus or minus 2i over 2 times 2, which would give us minus 1 over 2 plus or minus I over 2, which would imply alpha is minus 1 over 2, beta is 1 over 2. So the complementary solution Something just crossed my mind here. I'm going to go back and change the sign in the previous problem. So I think now this particular problem can simplify relatively easily. But we can leave it as is. So the complementary solution, back to our problem, yc is e raised minus 1 over 2 x times cosine x over 2 c1 plus c2 sine x over 2. So what we have here is e raised minus x over 2, c1 cosine x over 2, plus c2 sine x over 2. Now the particular solution. So the Wronskian we have y1, y2, but we shouldn't forget about that e raised minus x over 2 outside. So we have e raised minus x over 2 cosine x over 2, e raised minus x over 2 sine x over 2. Now we can, before we proceed, since we have, well, we still have to take the derivative using product rule. So e raised minus x over 2 times 1 over 2 minus sine x over 2 plus cosine x over 2 e raised minus x over 2 multiplied by negative 1 over 2 over here, e raised minus x over 2 1/2 cosine x over 2 plus sine x over 2 e raised minus x over 2 times minus 1/2. Now, before we complicate this problem with all sorts of cosines and sines, one of the nice properties of matrices is that if we have a constant term or like terms, we can pull that out. So first row, I'm pulling e raised minus x over 2 out. From the second row, I'm going to pull e raised minus x over 2 over 2. And that would give us cosine x over 2, cosine x over 2 with a minus, and minus sine x over 2. And the second term would be sine x over 2, and we pull the 1/2 out, e raised minus x over 2 out, so we would have cosine x over 2 minus sine x over 2. So the determinant of w is cosine squared x over 2 minus sine x over 2 times cosine x over 2 plus sine x over 2 cosine x over 2 plus sine squared x over 2. Do not forget the term outside, e raised minus x over 2. Those would go away, and we would have sine squared x over 2 plus cosine squared x over 2 multiplied by e raised minus x over 2, which would simply be e raised minus x over 2. Now we move on to finding W1. 0 and 4 root x, and we would have that term I'm going to pull e raised minus x out, and I'm going to pull 2 out, or 1/2 out, and I'll simply have cosine x over 2 minus sine x over 2. So the determinant of W1 is e raised minus x over 2 times minus 4 root x sine x over 2. U1 prime would simply be the determinant of W1 divided by the determinant of W. So we have e raised minus x over 2 minus 4 root x sine x over 2 divided by e raised minus x over 2. Those two would go away. We'll have minus 4 root x sine x over 2. Similarly, W2 would be e raised minus x over 2 multiplied by 0 4 root x, and the derivative that we have here is minus cosine x over 2 minus sine x over 2 and cosine x over 2. So the determinant of W2 is 4 root x cosine x over 2 e raised minus x over 2. U2 prime is the determinant of W2 divided by the determinant of W. E raised minus x over 2, 4 root x cosine x over 2 divided by e raised minus x over 2. Those two would go away. We simply have 4 root x cosine x over 2. Which would mean U1 is integral 4 root x sine x over 2 with a negative dx, and U2 is 4 root x cosine x over 2 dx. Unfortunately, this particular integral cannot be computed, reduced mathematically, so I'm going to replace x by t, or simply call it t0 to t, 4 root x sine x over 2 dx. U2 is t0 to t, 4 root x cosine x over 2x dx. I'm simply using fundamental theorem of calculus. So the solution, or the particular solution, I'll combine them together. Y is e raised minus x over 2, c1 cosine x over 2, plus c2 sine x over 2, plus u1, which is minus 4 cosine x over 2 integral t0 to t sine x over 2 dx, plus 4 sine x over 2 integral t0 to t times root x cosine x over 2 dx. I'm going to rewrite all x's by t's, so we have e raised minus d over 2 c1 cosine t over 2 plus c2 sine t over 2 minus 4 cosine t over 2 integral t0 to t sine t over 2 root t dt plus 4 sine t over 2 integral t naught to t root t cosine t over 2 dt. So here we have a third order dE. The associated homogeneous equation is m cubed minus 2m minus m plus 2 equals 0. Oh, sorry. Y triple prime minus 2y prime minus y prime plus 2y equals 0. And this would be the auxiliary equation. So the roots here we can factor this. If we pull m squared out, we have m minus 2 and minus 1 out. M minus 2 equals 0, which should imply m squared minus 1 times m minus 2 equals 0. M plus 1 times m minus 1 times m minus 2 equals 0. So the roots are m minus 1, m2 is minus 1, and m3 is 2. The complementary solution is y equals c1 e raise x, c2 e raise minus x, c3 e raise 2x. Now we have to find the particular solution. The process is exactly the same as the previous problem, but here, or the problems that we have done before, but the only difference here is we have 3 solutions there. So the Wronskian would be 3 by 3. We have 3 solutions because this is a third order dE. So the Wronskian W is e raise x minus, e raise minus x, e raise 2x. Got to take the derivative. That would be e raise x, and over here we would have minus e raise minus x, and e raise minus x, e raise 2x times 2, e raise 2x times 4. Nice thing about determinants, again, we could pull items, common terms out of the determinant. So I'm going to pull e raise x out, e raise minus x out, and e raise 2x out. That would give us 1, 1, 1, 1 minus 1, 1, and 1, 2, 4. So we have e raise 2x multiplied by 1 times negative 4, negative 2, minus 1 times 4 minus 2, plus 1 times 1 plus 1. E raised 2x minus 6 minus 2 and plus 2. So we have minus 6 e raised 2x. So if we have identical terms, like terms in the rows, in the columns, we could simply pull it out like I did, and things become pretty straightforward. Now we've got to find W1 and its determinant. So 0, 0, e raised 4x, e raised minus x, minus e raised minus x, e raised minus x, e raised 2x, e raised 2x times 2, e raised 2x times 4, Same rule as before. I'm going to pull e raised minus x, e raised 2x out. I have 0, 0, and 4x. And 1 minus 1, 1, 1, 2, and 4. So you can either take the determinants by rows or by columns, and you just have to keep track of the signs. So it's plus, minus, plus, minus, plus, minus, and plus, minus, plus. And the cofactor matrix that we use in finding the determinant would be that, and the term would be that. So the determinant here, the rest would become 0 since we have zeros. 4x times 2 minus of minus 1, which would be plus 1. We have 4x times 3. That would be the determinant of W1, which would imply U1 prime is W1 divided by, or determinant of W1 divided by the determinant of W. So 4x times 3, erase x, shouldn't forget the erase x out, and divide it by minus 6 erase 2x. I knew I was missing something here. That's not just 4x, it is erase 4x. Looked silly for some reason. So 3 erase 5x divided by minus 6 erase 2x. We have negative 1 over 2 erase 3x. The determinant of W2, we could find it first by finding the matrix. So erase x, erase x, erase x, 0, 0, erase 4x, erase 2x, erase 2x, and that's times plus 2, and erase 2x times 4. So erase x out, erase 2x out. So we would have 1, 1, 1, 0, 0, erase 4x, 1, 2, 4. Again, using a bit of matrix trick. So we're trying to find the determinant using that. And all we have to worry about is that term over here, and the matrix that we would consider would be 1, 1 and 1, 2. So the rest would simply become 0. So in short, we have erase 3x. Oh my. Erase 4x with a negative because the sign here is negative. And we find the determinant of 1, 1, 1, 2. So we have erase 7x times 1, which is simply erase 7x. So U2 prime is determinant of W2 divided by the determinant of W. That would give us negative 1 over 6 erase 5x. And lastly, W3 would equal e raised x, e raised x, e raised x, e raised minus x, minus e raised minus x, e raised minus x, 0, 0, e raised 4x. Now we are looking at that row, that column, so the cofactor matrix would be that. So what we have here, we can pull out e raised x and e raised minus x out, and we would have 1, 1, 1, 1, minus 1, 1, 0, 0, e raised 4x. So that would mean the determinant of W3 is simply e raised 4x multiplied by minus 2. This would imply U3 prime is W3 by determinant of W3 divided by the determinant of W. So minus 2 e raised 4x divided by minus 6 e raised 2x. Those two would go away. We have 1/3 e raised 2x. So those are the three functions. So u1 would be the integral of the first term, which is negative 1/2 e raised 3x dx. And that would simply be e raised 3x over 6. u2 is integral of negative 1 over 6 e raised 5x dx. That would give us negative 1 over 30 e raised 5x. And u3 is integral 1 over 3 e raised 2x dx. That would be 1 over 6 e raised 2x. So the particular solution here is yp equals u1 y1, u2 y2, u3 y3. So we have negative e raised 3x over 6 times e raised x plus negative e raised 5x over 30 times e raised minus x, e raised 2x over 6 times, what was it? I believe it's 2x. So we end up having negative e raised 4x over 6, negative e raised 4x over 30, plus e raised 4x over 6. Combine the terms together, those two would go away, and we'd simply have negative e raised 4x over 30 as the particular solution. And if we combine them all, the complementary solution is y equal, and the particular, c1 e raised x, c2 e raised minus x, c3 e raised 2x minus e raised 4x over 30. And that would be the final answer. Is it a minus? Yeah. Ooh, this is positive. So that would be positive. Which would make that term positive, that positive. So it would be plus e raised 4x over 30. Okay, So the key difference between a third order D and all the second order Ds is that the process is the same with variation of parameters. The matrix size would keep on getting bigger and bigger. So beyond a certain point, we simply use computers to compute all of these. Doing it manually would be quite cumbersome. And that is how we find solutions using variation of parameters.